on example number 3 for indeterminate forms and L'Hopital's rule, there's 3 other ones that are common to each other. They all have powers, which is a base and then an exponent. So when I was trying to teach this to students, trying to get them to remember these 3 indeterminate forms, what came to mind, to me at least, is this caterpillar type shape from the 3 indeterminates written together. So the 3 ones that are written together is 1 to infinity, infinity to the 0, and 0 to the 0 power. So if we do our initial plug-in for a limit problem and we get one of these 3, then we would know we have to apply L'Hopital's rule, and then to rewrite it so that we get a fraction that we can see is either 0 over 0 or infinity over infinity, and then at that point apply L'Hopital's rule. So where does this caterpillar come into play? So, and I don't know if we can think of it as almost like a cute caterpillar, where you have the tail end is at this point, let's say that's its tail, and then it connects to, that's its body here, and then can you guys see the eyes and the nose right there? Okay, there's my cute little caterpillar. Okay, and those are my 3 indeterminate forms with 1 to infinity, infinity to 0, and 0 to 0. So the first example, let's see which one we get. We have limit as x approaches infinity of x to the 1 over x power. So if I do my initial plug-in, I have infinity as the base, and then 1 over infinity we now should know is 0. So infinity to the 0 is definitely one of those indeterminate forms. It's the middle of that caterpillar. So when I think about these types of indeterminate forms, I'm going to ask myself, how do I bring the exponent down? And in order to do that, I have to apply an ln to that expression. So what we do is we're going to ln, but keep in mind, if we take the natural log of something, we're going to have to exponentiate or take e to the power of that to undo it. So think about, if I do e to the ln, they kind of undo each other, and so the expression that you have left is mathematically equivalent. So I would say that these 2 expressions are equal to each other. Whatever's in that box on the left is equivalent to whatever's in the box on the right. So here, if I take e to the ln of that initial expression, this is mathematically equivalent to the original problem. So what ln of that expression inside the limit does, the argument of the log, I can bring the exponent down. So let's rewrite that. I kind of like having the e there just to remind myself that at the very end I have to think about that. And so right now we're just considering the limit part problem first and ignoring the e. So we're going to bring the 1 over x down in front of ln. Okay, and so we have ln of 1 over x times ln of x, which is pretty close to being a fraction. So now we rewrite this as a fraction. So ln of x over x, and then plug in infinity at this point. So if we plug in infinity and evaluate, we have ln of infinity. Remember, the infinity graph is a really slow growing infinite graph. So infinity over infinity. So at that point, since we've come back to one of the 2 original forms, we're going to take the derivative of the top and get 1 over x, the derivative of the bottom, which is 1, and then simplify and try our plug-in again. And so if I do limit as x approaches infinity of that expression, 1 over x, if I plug infinity in, is equal to 0. So e to the 0 power is my solution, which ultimately becomes 1.